So in this video I want to briefly talk about some improvements that we can make to decision tree algorithms and also some of the challenges with decision tree algorithms. For example, overfitting and some tricks of how we can deal with overfitting. One potential improvement that we can make to decision trees is the so-called gain ratio, and this was defined by Quinlan. And if I recall correctly, this was in the ID3 decision tree algorithm. So essentially this is a modification of the information gain. So this is the information gain. And what's new here is that there is a denominator now. So there's a scaling factor, 1 over the split info for scaling the information gain. And the idea behind this scaling by dividing by the split info is that it penalizes splitting categorical attributes with many values. So if you have a categorical variable that has a lot of possible values, then this will be a penalty for the information gain. Because the split info will be larger the more categories you have in a feature. And the split information is measured as the entropy of the feature. So recall, before we always talked about entropy as the entropy of the class labels at a given node. So here it's the entropy of the feature variable. And we compute it as follows. It's essentially the same equation as for the Shannon entropy, or just entropy. But again, now it's on the feature instead of on the class label. So let's assume we have a feature with 10 possible values. So if we have a node and we split it into 10 subnodes and so forth, then and let's assume that the features will be uniformly distributed, then we have, for simplicity, let's say 1/10 of the data points at each node, so it's uniformly split. Each node we have now 1/10 of the examples, so that would be 1 over 10. So what we have is then for each child node, for the split info, we have a 1 over 10 times log 2, 1 over 10, and then the minus here, and we have that at 10 nodes, so we can just multiply this whole thing by 10, right? So instead of having the addition, we just do it 10 times, we add it up 10 times, and because it's negative, we subtract it 10 times. So in that case, what we would have is 3.32. So for a feature with 10 possible values where everything, for simplicity, is uniformly split, we have entropy or split info of 3.32. So we would then divide the information gain by a factor of 0.332. Now let's say we increase the number of feature values to 100. So instead of 10 we have 100 now. So what happens is, now let's write this down. We have 100 times 1 over 100 times log 2, 1 over 100. And this would be then, so if we ignore this for now, and this is the same with 100, this would be this value times 2, right? Because this is a log 2, and we have now 100, so we would have 6.64. What happens is, so if we have 10 times more features, because of this log, it will double the entropy. So, but even without thinking about concrete numbers, what that means is the larger the number of values for a given feature, the larger the split info, and the smaller the gain ratio, because the split info divides the information gain. So in this gain ratio, it takes into account how many values a feature has. Well, and why is that useful here? It has been shown, as I recall correctly, that this helps. For example, it helps also with avoiding overfitting. If we have a column that has a lot of potential feature values and we make these very wide trees by splitting on one feature instead of taking multiple features into account when we build a decision tree to make the child nodes pure, then yeah, often using one feature over multiple features is not such a good idea, and it is yeah, more prone to overfitting. So maybe the worst case scenario that we can think of is like something like a row index. So imagine we have our training data set with all the feature values, and then we forgot to take the row index out of the data set. So this will be then our feature x0, and then every feature will have a unique row index, and this would be a very good splitting criterion if we use a regular information gain. But yeah, in terms of the gain ratio, of course this would be a very bad feature, because it would be a lot of categories. So in fact, the number of categories will be equal to the training set size. But of course, this would also be a bug or a mistake in our data set. So hopefully we don't have a mistake like that where we encounter like a row index in our data set. Yeah, but still the same concept applies. So the gain ratio, this favors feature columns with many feature values. Yeah, and while decision trees seem to be very good classifiers and seem to be pretty straightforward, they also have a couple of downsides. So here's one of the shortcomings of decision trees. So consider a data set with two features, x2 and x1. And again, this is just because we can easily visualize a two-dimensional data set. It would be very hard to visualize a higher dimensional data set, although in practice we often have high dimensional data sets. So consider a case like this, where we have a data set with two classes, like these circles and these triangles. Now in this case we can see that a diagonal like this would perfectly separate these two classes. And I can write this diagonal as a very simple equation. For example, if I would look at this spontaneously, let's say this would be a perfect diagonal. What I could write is something like, or let me make a small modification. Let me tell you this is feature value 0, this is feature value 1, and this is also 1, so that it's maximum. And then I could write down a rule like if 1/2 of x1 plus 1/2 of x2 is greater than, let's say, 0.5, then class 1, or let's say class triangle, otherwise class circle. So if I have something like this, I would have a combination of the two features, and I could easily draw this diagonal as the decision boundary. However, with the decision tree, you remember that it is splitting the features perpendicular. So a decision tree split could be like this first, so for the first node, and then for the second node it could then split like this and so forth. So if I would draw that, it would look like a staircase. So it cannot do the diagonal directly, because the decision tree can only fit or split one feature at a time. It cannot split on a combination of features. So we can't have like this a linear combination of features. It can only split at one feature at a time. Of course, we could manually create combinations of features, so we can have a feature combination like x1, x2 and so forth. However, this would not really solve the problem. Also, in practice it would be pretty infeasible to find all these combinations of features. So in practice, if we would just apply the decision tree to a data set like that, it would make this staircase-like decision boundary. And each staircase here, so the first one, the second one, the third one, fourth one, fifth one and so forth, it would be another level of the decision tree. So in this case, it would be a super deep decision tree splitting the data set, which would be a super expensive model, and also kind of prone to overfitting. Also because you have to keep in mind it depends on how we decide the splitting bins. So if it could happen, for example, that the bins are super close like this, something like this, where they go up very close to the edges of the training examples, and then it also would be more prone to overfitting compared to a diagonal that is just in the center between those two. So that would be one downside of a decision tree. It doesn't do well with like these diagonal decision boundaries. It can only approximate the diagonal, but it cannot really make the diagonal directly, because it cannot consider combinations of features, only one feature at a time. So another downside of decision trees is that they are prone to overfitting, like I already hinted at in the previous slide. So overfitting means that it fits the training set very well, so it has a very good performance on the training set. However, when there's new data, even from the same distribution, it won't fit so well. So let's say the test data, usually overfitting is or can be seen by having a good training performance but poor test set performance. And in the case of a decision tree, assume we start at a certain accuracy here, and let me choose blue here, and then the deeper the trees become, the higher the training accuracy, so the better the model performs on the training set. However, when we then would evaluate the performance on an independent data set, for example the test set, we would see that the performance becomes worse on the test set. So first, also it increases. So here the performance on unseen data increases. This is kind of logical, because if you just do one split, or at the beginning at the parent node here, then you will have, of course, not as a good performance as if you have a certain number of splits, if you have grown your decision tree with information gain. But then if you split more, let's say here, this point is like here, and then if you split more, if you split it further and make it deeper and deeper, and deeper everywhere, or just in general deeper, then at some point here you will have this point where you see that the test accuracy goes down. Although the training accuracy goes up, the test set performance is actually worse than it was here, so it's now smaller. So that's the effect of overfitting, and that usually happens if the trees become very deep. And as I explained before in the previous video, when we have information gain impurity measures like entropy or Gini, then this kind of encourages the tree to make a lot of splits, and the more splits we have, the worse the performance will usually become on independent test sets or data sets that the model has not seen before in the training data set. So in one of the ways that we can address overfitting is by pre-pruning. So pre-pruning here means that we prune the decision tree before we grow it. Essentially it is related to early stopping, that we stop making the decision tree deeper. And many of these pre-pruning techniques are implemented in scikit-learn. So one very, very simple pre-pruning technique is just setting a depth cutoff. We can say, let's say the tree maximum depth is 4 or 5. It shouldn't be deeper than, let's say, 4 or 5 levels or splits. So we set that a priori before we start training. And you can also think of it as a hyper parameter that you have to manually find. So you would compare different tree depths and then just see how well it performs on a validation set. So again, you would use the training set for fitting the model, and then you have a validation set. So there you test your model, and you can try it for different max depth settings, and then you can see which model performs best on the validation set. And once you're done, you can get the final performance on the independent test set, so final model performance. And then after that, and another way, instead of using a validation set, is by cross-validation, k-fold cross-validation, and that is a topic we will discuss later in this class. But the simple way would be using 3 data sets, one for training, one for validation, and one then for the final model testing. There's another flavor that is related to setting the max depth, is cost complexity pruning. And cost complexity pruning, we set the total number of nodes also as a tuning parameter. And just seeing this sentence doesn't really make sense. I'm not sure what I was writing here. Anyways, the cost complexity pruning is setting a maximum number of nodes And another way is using a statistical test. So we do a chi-square test, for example, to see whether a split is statistically significant, whether it's a statistically significant improvement. And finally, a last possibility is setting a minimum number of data points for each node. So I think this one is not implemented in scikit-learn, but the other ones are. I'm not sure about this one, but I think at least the maximum depth and the minimum number of data points for each node. So the first one and the last one are implemented in scikit-learn. And in the last video for this lecture, I will also take a look at the code examples. I will walk you through how we can implement decision trees in scikit-learn, and then we will take a look at the parameters again, and then we can also maybe come back to this and see which of the techniques are implemented. So the last one here is setting a minimum number of data points for each node, and this is again very similar to setting a depth cutoff. However, it's operating on the node level. So if you have a decision tree like that, you say there has to be a minimum number, let's say, of 3 examples at each node, and that will prevent making a pure decision tree if it's possible. So there could be a decision tree where there's a 1 and 0 and another 0, and here if you have a minimum of 3, this would not be given, the minimum of 3, and here also not, so this split would actually not happen then in this case. Whether or not it performs then better is a question that we have to ask by evaluating it on the validation set. So in contrast to pre-pruning, where pre means before, we have post-pruning. So pre means before, and post means after. I think these are Latin words, but I'm not sure. So post-pruning means pruning the tree afterwards, after it's built. So we build the tree first, and then we remove nodes after we grew the tree, after the tree model is finished. And it is, for example, implemented in C4.5 in this algorithm. Then there's also a method called reduced error pruning, where it's kind of similar, where nodes are removed using a validation set evaluation step. However, if we don't have enough data, if we have a very small data set for training, then maybe we can't afford setting aside data as the validation set, so that would be one downside if we have a very small data set. And lastly, one step is to convert a tree into a set of rules, and then pruning the rules, like removing certain rules from the rule set. Here's a sketch of how the second step works, so the reduced error pruning. So here I was drawing the basic concept behind it. So assume you have drawn or created a decision tree that is pretty deep, like this. So in the reduced error pruning, what you would do is you would go back and remove individual nodes and see if that improves the validation set performance. So you would, for example, just remove this node and this node, and then see whether this improves your performance. And if yes, you would go one step further back and so forth. So you go steps back, you just remove nodes. Maybe you remove those 2, but you leave these 2 here. Or you remove these 2, but leave these 2, and so forth. And usually in practice, what you can see is that the validation set accuracy recovers. So when you are growing the tree, you may observe that the validation set accuracy goes down. However, when you do the pruning, you see that the validation set performance improves again. So this is the pruning, and you can see that even though you reach the same tree depth at a certain point, you will find that the validation set accuracy is actually better than it was before, because you are selectively using or removing certain nodes. So the tree depth is just like approximate measure. Maybe here it's easier to think of it as the number of nodes instead of the depth, because you can then create this as asymmetric tree where you have still in one node a very deep tree, but in the other ones you may selectively remove certain nodes and so forth. And that would be another way of improving the decision tree accuracy in terms of preventing overfitting and having a better generalization performance. Yeah, decision trees can also be used for regression analysis, especially like the CART trees, because as you remember, CART stands for classification and regression trees. So instead of using information gain for growing the decision tree, we use a concept called variance reduction. And if you go to the Wikipedia page for decision trees, it has a section on variance reduction, and it's very complicated somehow to read this equation that they put in there, and also the not all the letters in that or symbols in there are defined, so it's kind of impossible to read this equation. And however, it can be shown that what the variance reduction is can be expressed as minimizing the mean squared error, which makes it a little bit simpler. So essentially, the decision trees for a regression are minimizing the mean squared error at a given so let me write this out properly. We minimize the mean squared error at a given node t. So the MSE can be written as 1 over the number of data points at this node, nt, that's the number of n data points at node t. We have a sum over all the data points, I, for I over n, so this is all the data points, let's say nt, for the data points that are actually in this data set. So d is the data set. So let's say we have the sum over all the data points I over n, and for all these data points we compute the class label, or no, sorry, it's not a class label, it's actually a continuous label because we are in regression now for the ith data point. So this is the target value minus the model prediction. So H is our model, and then the model takes in the feature vector for the ith training example, and that is of course for the tth node, and then we square it. So this is the mean squared error, because we just compute the difference between the target and the prediction at the given node. So how do we compute the prediction? So the prediction itself is just the average, the node average. So if we have a feature vector at node t, so this would be just the average target value. So this is analogous to doing the majority voting. So if we have a given node here and we have different values, let's say this node we have the values 1.1, 2.2, 2.1, 3.2 and so forth, we would just compute the average here. So this would be the average, and the average would be our prediction at that node. And then we just compute the mean squared error there, mean squared error between the true target value and the mean target value, and that is what we call then the variance reduction. And sometimes people also call it the within node variance. So this is analogous to using entropy in the information gain equation. Okay, so to summarize everything we learned so far about decision trees, So focusing on the pros and cons of decision trees. One nice aspect about decision trees is that they're easy to interpret and easy to talk about. So if you have collaborators and you work on a machine learning project, if you show them a hopefully short decision tree, it's kind of easy to understand what's going on there, and it's easy to explain how the predictions work in the decision tree. And it can represent a complete hypothesis space for binary functions, so it can learn all the binary functions in a hypothesis space if the features are binary feature variables. However, one downside is that it can easily overfit the training data, especially because if you are not careful, decision trees will be very deep, and that would then require pruning, which can be annoying or also expensive. And then also we have seen in this staircase scenario that a decision tree is not very good at fitting a diagonal line. It would approximate it with these staircase, which is not ideal either. And in the regression tree examples, it would be one downside would be that the output range is bounded. And with that, what I mean is, if you have a data set, let's just say this is y is our target with only one feature, x, and then we have something like this as our data points. The decision tree for regression may look like this to approximate this. However, it cannot go outside the range of the training data. So let's say you collect later on a data point that is on the x-axis somewhere here, or it's, let's say, here. What a decision tree would do, it would still, in this case here, predict the minimum value in the training set. And here, in this case, it would predict the maximum value in the training set. It cannot extrapolate outside, for example. So if you have a case like, let me do a new plot here. If you have a case like where you have something like this, which would be perfect for a linear regression, the decision tree would again do the staircase to approximate this. However, now for linear regression, if we have a data point collected, let's say here, for a new data point that was not in the test set, it would still correctly predict that because it can extrapolate. A decision tree would, for this data point, predict this y value here. It cannot go outside the range, which is one downside when you use it for regression. So lastly, let's take the decision trees and recap some of the machine learning classifications or categories. So decision trees are a supervised learning algorithm, and they can be used for both classification and regression. And the optimization method in decision trees, at least in CART, this would be then maximizing information gain. Is it a eager or a lazy learning algorithm? So KNN was a lazy algorithm. So a decision tree is an eager learner. It does the learning during training. It doesn't wait until prediction, until it does all the work. It does work both during training and prediction, whereas KNN is a lazy algorithm, which doesn't do any training really. Another way of looking at machine learning algorithms is whether it's a batch or an online learning algorithm. So batch learning means that it requires the whole training set for learning. And online learning means that it can learn one training example at a time. So there's a special case. You can think of a linear regression, if you're familiar with that, and stochastic gradient descent. So in that case, you can update the model parameters one at a time. So you have, for example, a new training data point. Let's say you have a web app or something and you collect one more customer and you want to incorporate the customer into updating your model. You can do that with, let's say, linear regression and stochastic gradient descent. However, for a decision tree, you cannot just simply add a new training example to the decision tree. You would have to retrain it because it can change the whole model, right? So for a decision tree, it's not that straightforward to update it. So in that case, it's a batch learning algorithm. However, I just recently saw on arXiv that there are some online learning decision tree methods. In particular, just today I checked some arXiv articles. I'm one of the machine learning moderators there, and I'm sometimes reviewing some articles, like checking whether in the right category, and I saw one paper submitted on online decision trees, which is basically a decision tree algorithm that can be updated. I should maybe share that with you. There's an online decision tree. Hope I don't forget this. If I forget this, please remind me, because there was one student I remember on Piazza who was asking about newer decision tree papers. So this paper is not out yet because it was just submitted to arXiv today, so it will be out in 1-2 days. So I approved it, so it will be out in 1 or 2 days, and then I will share the link with you once it's available. So then we have parametric versus non-parametric. Parametric means that there are parameters that we it's a fixed size model and parameters that we update. For example, in linear regression, we have weight parameters and a bias. So the weight parameters are the model parameters, and there's a bias unit, which is technically also a weight parameter. It's basically the intercept term. And we learn these from the training data, but the number of parameters is fixed. So we are just updating the parameters of a model, of a parametric model. In a decision tree, and also for a k-nearest neighbor model, we don't really have model parameters. And you can think of the decision nodes as model parameters. However, it's still a non-parametric model, because you can an easy way to think about what's non-parametric is when you don't define the number of parameters up front, but the number of parameters depends on the size of the training set. So for example, in k-nearest neighbors, it becomes more complicated the more training examples we have, because you can think of, I don't know, if a training example is maybe as a parameter, but the larger the training set is, the more parameters we would have then. And also for the decision tree, the larger the training set, usually the more nodes we have. So in that way, we don't have a fixed size of parameters. The parameters really depends on the training set. And in this case, this is why we have a non-parametric model. And then lastly, whether it's deterministic or stochastic. So there is no stochasticity in the decision tree necessarily. So there's, unless there are some algorithmic tweaks, there's no way there's some randomness or random variables involved. So we don't have any random variables in the decision tree. So it's in that case also a deterministic model, similar to the k-nearest neighbor method. Okay, so that was decision trees. So in the last video, I will give you a code example how we can implement decision trees in scikit-learn, and there will be a homework where you have to implement a card decision tree by yourself, so doing it from scratch. I coded a decision tree in card myself, and I kept it very simple, and I will remove some of the functions for this, and you will be asked to complete the code to have a working version of a card decision tree, to kind of learn how to understand, to kind of learn how this works, and also to practice implementing algorithms, because that's a very useful skill in practice. If you, for example, do research later and you want to develop your own algorithms, it's very useful if you can also implement it in code, because in machine learning there are theoretic machine learning papers, but often even in addition, if you have a theoretic paper, people want to see that it works well in real world scenarios on real data or benchmark data. So you will eventually have to implement your algorithm and then test it on some data sets.